Hello everyone, this is Isha Kumari from Sri Venkateshwara College of Engineering, Bangalore, from the Department of Computer Science and Artificial Intelligence, and today I'm going to talk on the topic QuickSort and its time complexity. So the contents are as follows: Introduction to QuickSort, Overview, how QuickSort works, QuickSort algorithm, time complexity, advantages and disadvantages, and conclusion. So the introduction. QuickSort is a popular sorting algorithm that follows the divide and conquer approach. It is known for its efficiency and is widely used in various applications. The algorithm works by selecting a pivot element from the array and partitioning the other elements into two subarrays based on the relationship with the pivot. This process is then recursively applied to the subarrays until the entire array is sorted. Overview. QuickSort is a versatile sorting algorithm known for its speed and adaptability. It can handle various data types and is commonly used in practice due to its average case efficiency, ability to be implemented in place, and good performance for diverse datasets. It works by selecting a pivot element from the array and partitioning the remaining elements into two subarrays based on the relationship with the pivot. This process is recursively applied to the subarrays until the entire array is sorted. So how QuickSort works? First, we choose a pivot, select a pivot element from the array. The choice of pivot can vary, such as selecting the first, last, or middle element. The efficiency of the algorithm depends on how well the pivot divides the array. So the next step is partitioning. Rearrange the array so that all elements less than the pivot are placed before it and all elements greater than the pivot are placed after it. This step ensures that the pivot element is in its final sorted position. So the next step is recursive sorting, recursively applying steps 1 and 2 to the subarrays formed on the left and right side of the pivot. Keep dividing the array into smaller subarrays until each subarray consists of only one element, which is already sorted. So the next step is merge sorted subarrays. Merge the sorted subarrays to obtain the final sorted array. So the key idea behind QuickSort is the partitioning step, where elements are implemented around the pivot. This step ensures that the pivot element is in its correct sorted position. The recursion and merging steps handle the sorting of the remaining subarrays. The efficiency of QuickSort primarily lies in its average case time complexity, which is O n log n, where n represents the number of elements to be sorted. This makes QuickSort highly efficient for large data sets. However, in the worst case scenario, QuickSort can have a time complexity of O n raised to the power 2 if the pivot selection is consistently poor, leading to high unbalanced partition. To avoid this worst case behavior, various techniques like choosing a random pivot or using the median of 3 approach can be employed. QuickSort is known for its versatility, efficiency, and ability to handle various data types. It is widely used in practice and often outperforms other sorting algorithms, especially for large and diverse data sets. So here we can see an example where 70 is used as the pivot element, and the array is divided into two subarrays, and then again from those two subarrays one pivot element is selected, and again the partition is done, and similarly step by step the partition is done and the array is sorted. So the next is algorithm. So algorithm QuickSort A, L to R. So input will be subarray of array A, O to n minus 1. Output is subarray of array A, L to R, sorted in ascending order. If L is less than R, S is initialized to partition A, L to R. QuickSort, so this will be divided into two subarrays, QuickSort A, L to S minus 1, and QuickSort A, S plus 1 to R. And then algorithm partition A L to R, input subarray of array A O to n minus 1, output will be partition of A L to R. So P is initialized to AL, I is initialized to L plus 1, and J is R, and this is repeated. Then again repeat I initialized to I plus 1 until AI is greater than equal to P. Repeat the same for J, and then swap AI and AJ until I is greater than J, and then J will be returned. So here is an example of QuickSort. Here we can see that 4 is selected as the pivot element, and the array is divided into two halves, and then the process is repeated, and then after dividing the array into two parts, again two pivot elements are selected, and until and unless the array is sorted, this process is continued. So now time complexity. So what is time complexity? The time complexity of the quicksort algorithm is generally expressed using the big O notation. The average and best case time complexity of quicksort is O n log n, while the worst case time complexity is O n raised to the power 2. The average and best case time complexity of O n log n is achieved when the pivot element is chosen well, such as the median element, and the partitioning divides the array into roughly equal halves. In this case, the algorithm recursively divides the array into smaller subarrays, and the overall sorting process is efficient. However, in the worst case scenario, the pivot element is poorly chosen, and the partitioning consistently creates subarrays with only one element smaller than the pivot. This can lead to uneven divisions, resulting in a time complexity of O n raised to the power 2. This worst case scenario can occur when the array is already sorted or when all the elements are the same. It's important to note that the worst case scenario is relatively rare in practice, especially when using random pivot selection or other techniques to uh, address this issue. Therefore, on average, quicksort is considered a very efficient sorting algorithm with a time complexity of O n log n. So here are some examples of this time complexity, and here we can see that there is big O notation, omega notation, and theta notation. The best case is n log n, the worst case is O n raised to the power 2. So now the advantages. So it is quicksort is a divide and conquer algorithm and makes it easier to solve problems. It is efficient on large data sets. It has a low overhead as it only requires a small amount of memory to function. Disadvantages. It has a worst case complexity of O n raised to the power 2, which occurs when the pivot is chosen poorly. It is not a good choice for small databases. So it is a stable sort, meaning that if two elements have the same key, their relative order will not be preserved in the sorted output in case of quicksort, because here we are swapping elements according to the pivot's position without considering their original positions. So the conclusion. The conclusion is QuickSort is a powerful sorting algorithm that offers excellent average case performance. Its efficiency and simplicity makes it a popular choice for sorting large datasets. However, it is important to consider the choice of pivot and handle small subarrays efficiently. By understanding the inner workings of QuickSort, you can leverage its strength and make informed decisions when applying it to different scenarios. Thank you.